had come to my own conclusion earlier on. I had thought, well, because I was a ski instructor and I climbed as well a lot. I love climbing. And I was in nature all the time. I thought, well, if I want to know the structure of the vacuum, if I want to know the structure of space-time at the vacuum level, and if nature is being directed by that structure, I should be able to observe nature and see it. I should be able to deduct it from a good observation of nature. So I was always looking at snow crystals, and when I was climbing at the crystals on the rock, and I was always looking at things and the way branches divides in a tree and all this. And I had come to conclusions that the universal forces, the vacuum division, seemed to always generate a very fundamental, specific geometry, and that geometry was the geometry of a sphere. It makes spheres, little spheres, and bigger spheres, and then assembles them together and gets all sorts of things. But I was thinking, wait a minute, though. The sphere would be the part that's on the outside. The sphere would be the event horizon. The sphere would be the boundary from which things radiate. What I want to know is what's inside that. I want to know what's the geometry that holds the sphere together. How does the sphere pop out in the vacuum? And it wasn't obvious, but I started to study geometry and I realized that the sphere is the most unstable geometry. It's got the most surface and it doesn't have structure, so it's the most unstable geometry. So how would it hold together? And I thought, well, it has to have the most stable structure in the middle. And not only would have to be the most stable structure in the middle, whatever the structure was that was holding the sphere, that was dividing the vacuum, that structure had to be in perfect equilibrium. Because it had to be able to be observed as the vacuum. That is, if it had infinite amount of density, at the end of the day, when all the density, all the vectors of the geometry would collide at that level, the geometry that would result would have to be in perfect equilibrium so that we would think that it's empty space. That we'd think that it's a vacuum. So all that logic had come through, and so I started to study what would be the smallest, the most stable, the most equilibrium geometry I could find. And what I had found is that the exact opposite of the sphere, which is the largest and most unstable, was the tetrahedron. And if we look at a tetrahedron, it's made out of, it's the smallest volume possible, okay, with equal edges and equal faces. And it's made out of 3 faces on top and 1 on the bottom. So 4 faces generates, it's like a pyramid with a triangle base. And this is actually the most stable, fundamental, and the most fundamental geometric structure we can find in nature or in geometry. So I thought, well, okay, it probably has something to do with the tetrahedron inside a sphere. And I had come to those conclusions. So I didn't know why all these ancient people were building pyramids. But I thought maybe when I go home, I'll study it and research a little ancient text and stuff like that. So I go home. I'm living in Whistler, right? And I, went to my local library, which wasn't much. I mean, this is a ski resort. And I'm looking around, and this book pops out at me, and it's called Mystery of the Mexican Pyramids by Peter Tompkins. And I thought that was an appropriate title because I really felt there was some kind of mystery going on there. So I pulled out the book and I opened it randomly, if there is such a thing. And it opened on page 280, I believe. And it had this graphic on it. A tetrahedron inside a sphere. This was the first time I was starting to study ancient texts, and that's the first thing I found. Actually, the solution that I had come up with my own logic and my own geometry and my own math on my own. So I started to read, and I got the original papers, and I realized that this graphic came from the result of a 20-year investigation of the plaza and the pyramidal structures that are found north of Mexico City. And it has the moon pyramid, the sun pyramid, and the person that did the survey there, did it for the American Society, is known as Hugh Hollison Jr., I believe. And he came to very amazing conclusions. First of all, when he started to map the whole city at Teotihuacan, he found that the sun pyramid and the moon pyramid and all the other buildings seems to be in appropriate relationship to each other, so to reproduce a map of the solar system, including Pluto and Neptune, which were planets that we didn't discover in modern age until the early 1900s. So that was very amazing to him that these people would have that knowledge of that. It was very compelling. And he started to, he spent 20 years there surveying the whole thing, and he started to find that there was very specific ratio relationship between the buildings and how they were placed and mapped and all this around the world and around the whole city. And he thought, there's some kind of fundamental code that's being used here to build all this, and maybe there's some kind of fundamental message. And after 20 years of research, he delivered his papers to the American Society, and in it, he mentions that according to his mathematics and the way he mapped this, it seems that everything seemed to be pointing out that we should be looking, or that the mathematics that they use had to do with a tetrahedron inside a sphere. This really stunned me. It was amazing. I mean, I thought I was going to copyright that stuff, and somebody had come up with it a few thousand years before me. It was right there in this book, and so that really got me going in studying ancient texts. But more importantly, at the time, there was a comment that was made in that book that the fundamental equation that Hugh Hollison Jr. used to map this out matched a very specific mathematics of Buckminster-Fuller, which related to an isotropic vector metric. And the isotropic vector metric is made out of 20 tetrahedrons. There's 10 on the bottom, 6 on the second level, 3 on top, and 1 on top. It's actually a 4-frequency isotropic vector metric. This fundamental geometry was part of Bucky's concept that the universe had a mathematical geometric blueprint to it, so something very similar to my thoughts, and that blueprint related to this very specific metric. So I got very excited and I started to study it in detail. I looked at it in different angles, and I started to think, well, okay, so if I'm not dealing with just one tetrahedron, then there must be the interaction of the tetrahedrons may have different geometries involved in it. And since I was really investigating the structure of the vacuum, I was very interested in the negative space between the tetrahedrons. So I eliminated the tetrahedrons from the space and extrapolated what was in the middle of it, in between the tetrahedrons. And what I found is that what's in between the tetrahedrons is octahedrons, right? Now, an octahedron is a double bonded pyramid, okay? Emphasis on the word pyramid. This is the cavity between the tetrahedrons of the isotropic vector metric. Can everybody see them there? They're tilted like this, okay? And you could think of, for instance, if we look at this top one of the points of the pyramid is up here, the other point is back here somewhere, and it's on an angle somewhat like this, right? For you guys to look at. Everybody sees that? Oh, not quite, like this, right? Okay, so I was excited. Oh, here's the pyramids. It kind of linked with the ancient concepts. Okay, well, that's interesting. And then as I kind of traced all the vectors of the pyramid and in my drawings and in my head, I didn't have a computer at the time. I realized there was some strange negative cavities inside the isotropic vector metric. So here's our isotropic vector metric, and here's the cavities that I noticed that were inside it. Now, if there's 20, so let's put it this way, and if we look in between, there's our octahedrons, okay? But in red here, we've demarked that actually there is another set of tetrahedrons in the middle that are pointing inward, that are pointing down, right? And that are rotated from the initial metric. When I found those, I was surprised because this is thought to be an isotropic vector metric. I thought that must be the same everywhere. There shouldn't be any asymmetry. And certainly, I was looking for the geometry of the vacuum. So I was certainly looking for something that was in equilibrium and couldn't have asymmetry in it. So I was surprised. I didn't know what to do with these cavities in the middle. They didn't belong to the octahedrons, and they didn't belong to the tetrahedrons that were pointing up. So I thought, well, there's one thing for sure, is that if the universe is polarized, it cannot be that the geometry of space would have only one polarity of the equation. It would have to have both sides of the equation, and I had to add the reverse metric to it to get the polarity, the male, the female, the plus, the minus, the white, the black, and so on. So I added another metric below it, but when I did so, if I put one metric base to base to the other, if I put another one base to base to this one, then I have another problem. And that is, I don't get a sphere. I get an egg-shaped structure. And I was looking for the sphere. So this was like a chicken and an egg problem, and I was very confused. I was spending a lot of time on this. I'm walking you through things that took years because I was working to survive at the same time. Eventually, I quit my job, sold all my ski equipment so I could move into a van and sponsor my own research with very little cost. And so I was in my van thinking about all this. I didn't have a computer. So I've got these matrices in my head spinning, and I'm doing all this stuff with them. And I don't want to distort the geometry of the metrics. I'm not wanting to push them into each other. So I'm resisting that idea, and I'm trying to figure out how they would work. And then eventually, I came to it. I did push one into the other, which took me a while because I had to render all these vectors in my head. And I realized that when they would be in perfect relationship to each other, then I would get a perfect sphere. However, what got me extremely excited is that when they did, when I pushed one into the other and rotated so that it would be in perfect polarization to each other, the central red space that I didn't know were for what were exactly in the right position to accept the reverse metric without having me distort the geometry or remove tetrahedrons or anything like that. So that the polarized metric would actually be incomplete without its better half. And that when the second metric was inserted into it, it would take exactly the spot to create perfect symmetry at the center. And I was really excited because I was looking for perfect symmetry equilibrium. So I started to render in my head what is the geometry of these tetrahedrons coming in the middle. And that's when I realized that the result of the two metric intersecting with each other to create the perfect sphere generated in the middle what is called a cuboctahedron, which is 8 tetrahedron coming together, which was called by Buckminster Fuller the vector equilibrium, the only geometry in which all vectors are in equal proportion to generate perfect equilibrium. I had found the geometry of perfect equilibrium from the polarity of the two isotropic vector metrics coming together. Why is this geometry, for instance, the only geometry that's in perfect equilibrium? Well, I studied a little bit and I realized that actually, if you have vectors of forces and you want to create equilibrium, then you would have, obviously, now, this vector that just popped out could express a force. And we'd say that that force has this specific unit, which relates to the length of the vector. So bigger the vector, stronger the force, smaller the vector, smaller the force. If you wanted equilibrium, you'd send another vector in the exact opposite direction, at the exact same length, and you'd get equilibrium. However, this would be a very precarious equilibrium. Nature could not use that equilibrium because any distortion would make the vector collapse. Any forces in any other direction would break the equilibrium. So it was very unlikely that the universe used that type of equilibrium. Well, what would it do? Because this is unstable. What would it do? Well, if you were trying to get an equilibrium yourself, you would probably say, well, I'll just keep adding vectors. Well, if you add vectors at 90-degree angle from the initial vectors, you're still not going to get equilibrium because now what's going on is that the edge vectors are longer than the vectors to the center, so they're stronger, it implodes, it doesn't work. No equilibrium. So what would you do? You probably continue to add vectors, and you would probably put them at 45 degrees from the initial one. And now you have another problem, that is the edge vectors are shorter than the vectors to the center. Now the geometry explodes, is still no equilibrium. So what would happen is that you would have to make sure that the geometry's edge vector and vectors to the center are the same length. And the only geometry in which this happens is like the snow crystals, the hexagon, where the edge vectors are the exact same length as the vectors to the center. And if we made a 3D hexagon together, we would get a vector equilibrium, which is made out of 12 vectors radiating from the center and 12 edge-bounded vectors that maintains the structure in perfect equilibrium, or 8 tetrahedrons coming together, all right, to create, a vector equilibrium. So 8 of these coming together to create a vector equilibrium. And so that was really telling. That was really exciting for me. I knew this had to do with what I would have to deal with even if you think in advanced physics, for the physicists here, that, you know, of the structure of space, you could think that the vacuum state is going to infinity. At one point, it would have to reduce to the minimum amount of vector for stability. And that would be 12 vectors. So that's the fundamental, basic geometry of equilibrium. But it actually didn't fully work. That is, I still had points on the edge of my metric here. Right? I still had vertices on the edge of my metric that had holes in it. Right? So there was a symmetry. This middle structure with the 2 isotropic vector metric was completely filled, but the edge was not. So I had still a symmetry. I still didn't have equilibrium. So I started scratching my head some more, and I thought about it, and I thought about it, and I thought, okay, well, my only solution is to continue to add tetrahedrons until I get equilibrium at all levels. So I continued to add tetrahedrons. I covered the spaces that were open on the edge of the metric. So I had to add 3 tetrahedrons to every edge, which was 8. So that generated 24 more tetrahedrons. So remember, there's 20 tetrahedron in one isotropic vector metric. 2 makes it 40, plus 24, added up to 64 tetrahedron grid. And that, when it came to me. At 64, it all came together. Why is that? Because when I put those added 24 tetrahedron in my head as I was visualizing all this in my van, I realized what I had done. I realized that I had generated a vector equilibrium in the middle, but now I had generated a larger fractal vector equilibrium on the edge. And so now I had a metric that was growing from one vector equilibrium to the other, to the other, to the other. And interestingly, they grew in perfect scale of exactly half the radius, so in harmonic scales or in octaves, if you want. And it was a 3-dimensional fractal. This is actually one of the only true 3-dimensional fractal I believe exists. And it grew radially, which is what I needed for the radiation part. And then I realized something even more significant, is that the fractal growth could be generated from 8 star tetrahedron. So 1 star tetrahedron is 8 tetrahedrons coming together to make an octahedron in the middle. Everybody sees that? 8 star tetrahedron, 8 stars like that coming together, okay, to create the vector equilibrium, right? So 8 of these coming together to create the vector equilibrium. And when I realized that, I saw that the star tetrahedron is 8 tetrahedron pointing out, and that the vector equilibrium is 8 pointing in. And now I had both sides of the event horizon, the radiative side and the contractive side, all in one mathematical metric that was producing both to generate the feedback of creation. I was really excited then. I mean, People would, you know, anyway. My van was bumping around, you know, and it's not because I had a girlfriend. And so so I realized this, and it was like the 8 star tetrahedrons coming together to create the vector equilibrium in the middle. Just like this. And when the whole thing was put together, it would generate a vector equilibrium in the middle, right? The vector equilibrium in the middle. And then it would generate the next fractal vector equilibrium on the outside, right? And so it was a radial growth generating scale in the vacuum. So I was really excited. I thought I found something very significant. I was looking now to solve this and in terms of physics. How does it apply? How does it, you know, emerge in the physics? And as well, I was starting to think, well, this physics must have, you know, angular momentum, must have dynamics to it. This is not a static thing. This is a fluctuating thing. So how does that all compute? And, you know, I was doing research in advanced physics and all this. I came across a graphic on the internet of a phenomenon that's called crop circles. And that graphic was a perfect representation of the fractal structure of space I had just described and found in my van jumping around. Now I know that there is hoaxes out there and hoaxers out there, and I know they make crop circles at night with their gumboots and drinking moonshine and stuff. But there is as well a lot of genuine phenomenons that goes on with these crop circles, where it's not obvious to just write it off as people jumping around with gumboots, or Doug and Dave out there, you know, having a good time. What got me really interested is that there was a bunch of croppies, people that photographed these things and measured them and all this, that had gone into, you know, they figured out if somebody is trying to talk to us, whoever that is, maybe we should just try to talk back. So they got some gumboots and they went in there and they stomped around in big letters in their field. What do we need to know? And the very next crop circle that came out was this. And that really, you know, struck a chord with me. And if you look carefully, you can see that the way the crops was laid, it made an effect of light and shadow in which you could see the vectors of the tetrahedron that would be creating this metric in three-dimensional space. Now that's not obvious to do in the middle of the night, in the middle of a field. All right? This is not a small thing, it's a large thing, and it's very, very accurate. And then a few weeks later, they seem to insist on the pattern. Another one, just like the first one. And this one with another set of information in the middle. In this case, there was another set of fractal division that was going on in the middle. And when I looked at it closely, I realized that that set of information was the exact same structure of division, those triangle divisions of space, or these tetrahedron division of space, but in this case, pointing in the opposite direction, going inwards towards infinitely small. Never mind the fact that if I overlaid the octahedron part of the 64 tetrahedron grid over top the crop circle, it was a perfect fit. This compelled me to continue to study these things And as I was studying advanced physics and continuing to advance my theories, and I realized that there was eventually crop circles that were perfect representations of the 64 tetrahedron grid that were emerging in the crops of England. And then vector equilibriums coming out of the crops of England with singularities at their center, including the information about the boundary generated by the tetrahedrons, so that if you knew that each tetrahedron generates its own boundary, then you would add them here and generate this other geometry which has been popularized as the seed of life, and then a crop circle to tell you you've decoded right. And so this was like a code that was being given.